the AI people and HCI people having a meaningful relationship, not necessarily the users. I know the idea of academics having a meaningful relationship might be quite hard to get around, though.
Okay, so we thank Barry again. Thank you. So now we have Antti Oulasvirta. Well, I was practicing this yesterday with Airi, and she said I'm crap. Sorry.
Thanks, that's a good try.
It was a good try. There was a ooh. Anyway, Antti and I think we were annoyed by the same thing in our field, and then we took completely different routes, as Antti said. He took one route, and I took a completely different one. And I think actually he's the one succeeding. And so this is going to be super interesting to listen to where you are.
Thanks.
So, Antti.
Okay, hey. Thank you for organizing this. It's very important to keep discussion on AI and HCI. And I'm going to send first hellos from Helsinki. We have a group of researchers coming from 5 groups. We meet on a monthly basis and we talk about AI and design and so on. I come from a cognitive science background, and my own area now that I'm leading at Aalto University is called computational design and computational interaction. And this is just a gallery of the kind of stuff I'm going to talk about today. We use perceptual models of human, for example, to optimize visualizations. We can generate automatically, I'm going to show how, full user interface designs, such as hierarchical menus. This is a very hard combinatorial problem. We can infer parameters and, let's say, needs and capabilities of people and adapt interfaces accordingly using these models that we have mathematically expressed in a computer. We are using AI and computational methods in order to simulate user behavior better. I'm going to do a really blunt motivation here. So if you look at interaction design, and I guess most of you know that, it's a major profession these days in global technology industries. Most of it is manual, so it's very unlike to how, for example, many things are done in, for example, electronics or other forms of engineering design. And this, of course, has brought about the question that what could be automated in design. And here's one of the speculations. Albrecht and Susanne showed other ones. This is particularly for design. You see here that in this particular speculation that comes from Harvard Business Review, they thought that designers, they range from 5 to 15% of automation, right? But ideally, we should be looking at it from the perspective of HCI, meaning that we analyze work, we analyze design work and design tasks, and we analyze what is the achievable, realistic level of AI performance and what are the unintended consequences of that. So I want to take you one step closer with one methodology from AI to say, and I'm going to come back to this diagram and say something about it. This is, of course, an age-old question. We already heard about automation and so on. And also in the area of design, Nigel Cross has been speculating this since the 1990s. He has a really nice and undercited paper called Natural Intelligence in Design, where he compares artificial intelligence with natural intelligence, saying that, well, design is very different. Natural intelligence design is different because we need to be rhetorical, you need to explore. You have emergent properties, it's opportunistic, it's using abductive reasoning, it's reflective, it's ambiguous and risky by nature. And he was saying that, well, the AI of that era wasn't able to match these qualities. And he was saying that it's actually, we should not be trying to match these qualities, but rather we should be using AI as a vehicle to understand design itself. So he's writing that we should be help and inform understanding of the natural intelligence in design cognition and design ability. And this is in a way what I'm doing here. So in the rest of the talk, you're going to hear about combinatorial optimization, Bayesian optimization, and I'm going to show you how we already can achieve what could be called weak AI. Weak AI means that we're able to do certain tasks that are well specified and isolated, as Albrecht was saying, with quite high success rates. And with meaningful results. And then I'm going to talk about this point that actually it's a new theory of design and interaction. We're expressing everything mathematically in such a way that we can make those theories actionable. They produce verifiable predictions that are embedded in artifacts that are produced by the algorithm. And then I'm going to go back to the big boogeyman, which is the artificial general intelligence, which is, of course, the backbone for all these scary words about how robots are going to steal all the jobs of designers. I'm going to start light and just start discussing about other form of thinking. I guess most of you know design thinking, and I start with computational thinking because this is something that I teach to my computer science and engineering students. And I want to lead them to think about design from a computational perspective in order for them to work with math and code on it. So what is computational thinking? This is BBC's infographics that is showing that it has 4 elements. You decompose tasks, you abstract tasks so that you go beyond the particular instance of a design problem, which is often the focus of traditional design, so that you see the big forest behind it, and you can apply pattern recognition, and you can apply algorithmic solutions to systematically solve them. And of course, one of the benefits here is that you start understanding the complexity of design and complexity of interaction once you start addressing it like that. And of course, when you are successfully implementing an algorithm, you can replicate that en masse, and of course, also look at the consequences of scale. What happens when you have more complex interfaces, more users, and so on. We've been trying to define what this area is. So we're basically applying computational methods for design and interaction. And we define it in this book as applying computational thinking to explain, enhance, and learn from interaction with the human. And it's underpinned by modeling, and this is a key thing. I'm going to talk about models all the time. So models are at the core of our computational thinking and its applications. So these models are doing 2 things that are really important. First of all, they're touching with data, the outside world, some observations in order to update themselves. And then they must do something in order to adapt or synthesize or change the design that they're responsible for. This has the consequence that if you want to build on AI, you must embrace mathematics as your language, right? Because this is how all of them are implemented. All computational thinking ends up being code or math. Code is math as well. Now, if you look at it like that, then you find that there are actually many formalisms in HCI already. Already from the cybernetics era, you have logic, information, control, optimization, agents, learning, probability, neural networks. Eamon is going to talk about neural networks. I'm going to talk about optimization. And we just came up with this book, and it came out this year, and Kia was visiting, and she was the first person to whom I gave the book, and she lost it on the way back to Stockholm. So I brought you a new book. Yes. Yes. So what do we generally seek with these methods? So we seek scalability, we seek rigorous analysis of problems. We try to improve, of course, designs. We try to support the creativity of designers and adapt interfaces automatically, and of course allow new ways of controlling and customizing interface. I'm going to show examples of all of these coming from this optimization camp. One thing I want to make first clear is that there are many waves of AI, and if you look at the debate that we had today, even they refer to different eras of AI HCI discussion. There's this wave 0, which is cybernetics, which is blissfully forgotten. Kalle was sort of referring to that, but implicitly at least. And then there was the first wave, logic, then cognitive modeling. Everybody knows GOMS, and KLM was mentioned by Albrecht. And then there were like the 1990s machine learning wave that it was using like support vector machines and so on, and like user modeling. And now we have the second wave with deep learning, Bayesian methods, and so on. And I think accordingly we should be updating our debate about what AI is for HCI. And this is one attempt at doing that. So. I stole from Suzanne this word taming. So I'm going to talk how to tame methodology called optimization for the uses of design. And you're going to hear Eamon's talk about deep nets, and this is a very different approach. This is something where we mathematically try to express everything. And so it's an ultra-rational approach. And it's also what is called a white box approach. We don't have problems with interpretability because everything is there in code and clear. We don't hide them in millions of parameters like in deep nets. This is an idea that of course, wasn't invented by me. There were lots and lots of precursors for that. August Dvorak, who designed the Dvorak simplified keyboard, he was suggesting, he's a psychologist, and he was suggesting that we should actually use psychological theory more systematically to design, for example, like keyboard layouts. And that so he was hinting that the psychological theory should be the objective function that you use. While Herbert Simon wrote the Sciences of the Artificial, that was suggesting that we should be using theories and models and simulations in order to predict and speculate about possible designs and possible artifacts. And Stuckart, of course, he started with the GOMS model, and in his 83 book Psychology of HCI, then he was alluding to operations research that I think Kalle represents a little bit as a model for HCI as well. He never took the step of actually applying optimization. So he went to the modeling side, I'm going to talk about models as well, but never took the algorithmic step, which I'm taking here. So optimization is easy, and we do that intuitively all the time, also as people and as designers and so on. Ultimately, everything that I talk about boils down to a very simple idea, which is that you have a finite set of designs, that's the capital D, and you're trying to find a design, lower letter D, that maximizes some goodness function. You express in code what makes a good design. And you also have some conditions that we express with some parameters. Now, there's a little bit of math in this talk. I'm going to go back to this, but basically we're looking for a design in a set of designs that maximizes some goodness function. Now the question is, how do you formulate this design task? How do you formulate this goodness function? How do you obtain this condition, right? And in a way, everything that I do boils down to these three questions. And that's why you need help from psychology, computer science, and designers. So what's nice about it that everything that they contribute then comes back to code that is expressed like this. As I said, I didn't invent this. Like if you go 15 years back, this was state of the art. Just to illustrate how this works, this is a classic problem called letter assignment problem. You have a finite number of letters. You need to assign them to a keyboard grid. And you need to say that, well, this N goes over here, this P goes over there. And there's N factorial number of ways of doing that. Now, the question is, of course, what makes a good design? Now, the optimizer must have an explicit statement about that. That's called an objective function or goodness function. And here, in the classic work, we were trying to minimize words per minute, maximize words per minute or minimize the time that it takes for you to move your finger. They're basically the same. So how that works is that you have to minimize the time that you spend moving the finger, weighted by the probability of the letter transitions. For example, E and H are very common, Z and X are less common in English. So I would take that into account. And now you formulate like this, you can throw it to a solver. There are many, many solvers, and once you get to this point, the solvers will take care of the rest. Now, this approach can be extended, and there's a lot of work since the 15 years. And we can already, I would claim that we reached a state where we can generate actually usable interfaces that are put into practice. One of the things that I'm really proud of is that we work with the AFNOR, which is the French standardization organization, to redesign the AZERTY special character mapping. There's a very large number of characters. For example, in the French language, they have 6 different quotation marks. Now all of them must be mapped somehow to this keyboard, and that's a huge problem. That's a problem of this size. Just to give you a point of comparison, there's 10 to the power of 82 atoms in the observable universe. So this keyboard problem is way harder than finding an atom in the universe. And now the question is, of course, how do you formulate the objective function? In this case, we had very similar model as this one, but we added also ergonomic term, we added a learnability term, and a familiarity term. Now we could throw this to a solver, and we work with some optimization researchers to do that. And now it's been finalized, the new standard. Extending on this assignment problem, you can go to menus and hierarchical menus. This is what I teach to my students. You can take information foraging theory and apply that as an objective function that tells how people seek items in a menu. And now you can, all you need to give as an input is the frequency of items and associations between them. So you say that, for example, open and select are 50% associated, whereas open file and open location are 80%, right? And then the optimizer does the rest. And these are also very large design spaces, so these are exceedingly large for human designer to work on. These are optimized designs, and we compared them empirically in a controlled study against commercial baseline designs, and we beat them by 20 to 30% in search time. Here's another one. We can automatically generate nice visualization. We are implementing models of human brightness perception, contrast perception, unit formation, very basic laws of human perception. And then we ask an optimizer to choose the parameters of visual design. So this would be something that you get without the optimizer by default. And you can give a couple of seconds and the optimizer will give you this. This is work with Tino Weinkau from KTH. You can also use it inversely. So here you see we also work with game developers. So you can predict the probability with which a gamer will die in a particular level with particular parameters of the level, given the speed of the bird or the width of the pillars and so on. And then you can use this automatically to generate game level designs. Here's a gallery of other stuff that we've been working on, application menus. This is work by Christoph Kajos on widget controls. We were working on web pages and getting some pretty good results. I'm going to show them later. You can do gesture control optimization using this. Now I'm going to dwell a little bit deeper into what this optimization actually means. And I'm going to go back to this formula that I showed about maximizing the goodness. So you can think about optimization always working in a finite space of possible designs. Let's say that this is that bubble. And somewhere there are the best designs. We don't really know where they are yet. That's why we must search. And that search action is done by the solver. The solver has in it a definition of the decision task that it must take, what kind of decisions about the interface it must take, and what constitutes a good design, what is the goodness function. One thing is still missing, that's the theta that are the conditions of the particular design case, and that's called the task instance in the optimization lingo. And that can come from designers or users. I'm going to talk about how do we get these theta to the objective function. Now this looks very complex, and I borrowed Don Norman's design stool, and I made it the computational design stool. And on top of the stool is sitting a model. As in all computational approaches, there's some predictive model, and then we have the search process. We are searching over possible designs. We have an inference process where we try to get the particular parameters that describe this particular case. And then we have the leg for predicting. We want to predict the consequences of our design choices on users. So I'm going to go through all the legs and then come back to what AI can do for these legs. So optimization is basically a process of searching for desirable designs algorithmically. And there are many, many ways that can be done. And it's interesting if I go back to Nigel Cross's paper that I referred to in the beginning, and he said that, well, machines are designing in a way that you just give an input and it gives an output. But how designers are designing is they gradually go toward a better design, and they have they go through a series of sketches and drawings on the way there. And in a way, optimization is doing something like that. Inside the process of optimization, you can think of that there's a landscape. So on the y-axis, you have the objective or goodness of a design, and on the floor here, you have the design variables that are describing the choices that the optimizer must do. And in a way, what it's doing is trying to guess where the good designs could be. And it's trying to explore, so go to different corners, but it's also trying to exploit. When it finds a good peak, it tries to climb that. This is the way optimization works. It has some similarities to human design, but this can be done 1 million times per second. And that's why this is potentially particularly useful for cases where you have large combinatorial decision-making problems. And this is one takeaway, is that this is a class of problems in design that we can identify, we can well define, as Albert was saying, that those things that can be well defined can typically be automated. And we can define the different needs of users, for example, in finding menu items or using web pages. We can define different design objectives. I'm going to show you how, but we can define aesthetic things and performance-related things, error-related things. And we can deal with very large design spaces effectively using these optimization methods. And in a way, our group wants to build on this capability, but integrate that to the practices of designers. And here you see one demo that we had at Kai and was published at this. Here's a designer, actually our group member, using a design tool for wireframe design. And there are both local optimization, there are some local suggestions on how to improve the design on the right, and also global design, completely redesigns of the same thing. So what it does, it tries to detect or recognize what kind of tasks you're actually working on, and then in the background, the optimizer is trying to find alternative ways of doing the same thing. And then we, of course, tested this, and most of the designers, they picked at least one suggestion by the optimizer during the design process. But the optimizer didn't dictate what the designer should do. It's also a problem-solving toolbox. As you see, it's all expressed in math, and there are very powerful methods in optimization to talk about multi-objective optimization, how to trade off if you have usability versus security, or aesthetics versus usability, or errors, and so on. It has notions for robust optimization, so finding the best compromise among competing assumptions. It has methods for exploration, effectively finding alternative designs in the design space, and also for local optimization. Let's say that you have a particular product, users want to improve that by K%. Well, we can ask from the optimizer, is that possible, and what the design would be. So this was the first leg of the computational stool. The second leg is about prediction, and this is the key to what we do. We want to have verifiable and transparent predictions coming out from the system. And in a way, you can think about it as counterfactual reasoning. It's speculating. The algorithm is speculating given the model. So it's making a change to the design and asking from the model, what would happen if the design was like this? And the goodness function, the objective function, is saying that, well, this is what would happen. Right? So this means that this model should talk about human behavior, human experience, and so on. So what has been used, for example, in operations research and optimization research earlier, which is based on, let's say, physics and chemistry, we must now replace with behavioral and cognitive sciences and models that come from human sciences. Now, luckily, there are many such things. You know, you can go to design research and find design heuristics and models from there. You can go to psychology and find models of human perception, attention, and so on. They are sometimes expressed as mathematical models. Sometimes they are step-by-step simulations that you can then execute. Here's one example of a model that we developed for menu selection. It looks complicated, but actually the good news is that if you find one, now you can just implement this in code in a matter of a few minutes, and then you can exploit it as a goodness function in your optimization. Now, we struggle a lot to actually work with complex problems, and one insight for our modeling has been not to try to model the full cognition, full task performance of a person, but to sort of bound it. So we have lots of models of different bounds of human performance, human experience, and we try to say that, okay, this design, for example, will unlikely be faster than this. So something like KLM that Albrecht was using, was pointing out would be used for this. But then we also have models for different qualities of aesthetics and perception and so on. So we can also say that, well, people are very likely to perceive this as to be cluttered. And now, a good design is, of course, good in all of these respects. So what kind of models are there? There are lots of different bounds that can be implemented from psychology. They talk about how we perceive things, how we time things in temporal domain, how we perceive things to be salient, how we perceive things to be formed in terms of gestalt or units, how we search, how we use our working memories. All of this can be implemented now in code. And now you can ask from these models that, you know, how would people perform or experience a particular design. I'm going to give you this example. This is exemplifying what's very typical of these problems is that then if you only have one objective, let's say performance, then you typically produce garbage, and you actually have to take many different objectives. In this case, in the wireframe design, we had to have at least 6 objectives. So if you just optimize for clutter, you get something like this. If you optimize, you know, these are not final results, but just give you a hint of you know, single objective optimization being insufficient for design. So, but if you combine them, you start getting really nice results out of it. AI can also help us there. So what you probably know are cognitive models of this type, boxologies, where you have inputs and outputs going to different modules, and this was called the information processing approach, and this was part of the debate that we had about AI and HCI and the cognitive model failing. One reason why this has not been very successful in optimization was that these models didn't have ability to adapt itself. So if you change the design, you as a researcher has to describe the task, the way the user would solve a particular task explicitly to the model. And of course, that's impossible in the optimization context. You would have to have millions of those, right? So we need a capability, and then now this is given from AI research, to learn those task descriptions automatically. So just to illustrate, I'm going to show you a web page. Now the question is that if you're looking for political news, how would you search this page? Maybe you see it immediately, I don't know. But there would be many strategies. You could scan like this. Typically, people are using this kind of F-shape pattern. You could also look for them from the menu, or you could try to memorize, you could try to recall from a memory where it is. Maybe you would be driven by the salient features of the page, such as this one or that one, and look at over there, right? And over time, people develop and adapt their strategies, and we can predict those with what is called computational rationality. And this is something that is coming now from AI and cognitive science research. This is not the activity theory triangle, this is something else. Here we have behavioral space, and it's the strategy, the way we actually interact with the design can be predicted if we know the goals or utilities, the environment, and the capabilities of the user mechanisms. And they bound the space of good strategies, and then using machine learning techniques like policy learning, utility learning, Bayesian brain, we can actually make a prediction on that. Let me show you what that means. For example, it has been impossible previously to predict for any given design how users would search that, because we were lacking this capability. So now we have a model that predicts how people will search displays like this. If you're looking for, let's say, Excel icon or this icon, then the patterns will be very different. Also, if you learn the site, then you will have different strategies. So for this icon, you can immediately jump there if you know it's green. For this one, you need a little bit of location learning, right, and a couple of repetitions to get there. And we try to model those capabilities. And those capabilities are long-term memory, visual short-term memory, feature guidance, that are the features that you see with your fovea and parafoveal vision. And then, of course, all of this must somehow guide where you look next. And now with machine learning techniques like reinforcement learning and utility learning, we can make a prediction on how people would adapt the use of these strategies when they're looking for different targets, when they have different designs, and when they differentially learned with the device. These are just examples of looking for a novice user looking for icons, and then an expert user looking for icons. So now you can use this as a basis for simulation-based optimization. Another one I want to mention briefly, because I was just presenting this at CHI. There's a really interesting and influential idea from neuroscience. It's called the Bayesian brain hypothesis. And the hypothesis is basically that in situations of uncertainty, whenever there's imperfect knowledge or uncertainty, the brain is operating close to the optimal as prescribed or modeled or bounded by Bayesian statistics. And there's work in very, let's say, lower level aspects of human mind and human perception showing that there's some truth into this claim. Now, I want to show you this because we, now that you have generative models, you can actually drive a robot. This is a human-like finger that you can give any button to. So you can give a touch button, linear push button, tactile push button, mid-air button, and it learns to use it, and it produces human-like kinematics, movements, and use of force and precision in a task, and we can also estimate the effort. And that's all thanks to this learning capability that comes from Bayesian optimization. So it learns a way to use its own capabilities for its own goals. And you can change the goals. For example, you can ask it to be more energy efficient, or you can ask it to be more precise, and it's going to adapt the button press accordingly. And all of this is based on this Bayesian brain hypothesis, which is basically, you can implement this in no time. You can take this in MATLAB or Python. These are all well done. Basically how they work is that the model has no clue in the beginning about the world, about the way the motor commands that it sends are mapped to the sensations that it's getting back. But then, after one observation, it already has some improved probabilistic model of the world. And after, like 10 or 20 trials with the button, it has learned something like a human-like pressing of the button. So here's one case for using AI to actually better predict human behavior. Another one that I want to talk about is AI for inference. So this is when you go from empirical data to model. So we need that in order to optimize designs for particular users, particular tasks, and so on. And as you know, it's very easy to collect lots of data about people, but it's very hard to say what actually happened, how people solve the problems, why did they behave the way they do. So let's take an example that we are studying. You see click streams. So you see that a person is clicking here. Why would that person click over here? Was it that then the person was trying to open this, or slipped a little bit, or was trying to explore what's over here, or what happened? So even for a simple thing like this, there are already some explanation. Think about if you have a click stream full of such observation, then it becomes very complex. And the artificial intelligence methods, or machine learning methods more appropriately, are called inverse modeling methodologies. And we're using simulator-based methods that are simulator suitable. So basically we have simulators like the ones that I showed. And here's what they do. So normally when you do modeling, you construct a model and then you compare it against some predictions or some empirical data from the world. Now what you do is the opposite. That's why it's called inverse. So you have a user that produces this is a multi-dimensional space of all behaviors, okay? And it just produces one particular behavior. And we want to find theta. These are the parameters that are described in the simulator and the user that gets closest to this particular user. And now what you can do is you can, so this is one example that we did last year. You can have click times on a menu. Now you can ask from this Bayesian optimizer that is trying to do this inverse modeling, what are the human visual system parameters, HVS parameters, that best describe this user? So you have no information about that person, but just ask the most likely explanation. For example, what kind of use of semantic knowledge versus use of fixation information, what kind of fixation durations this person has, and so on. And now once you learn those parameters, what you can do is you can emulate that person again, right? So I learned from click times plausible explanations of that person using that simulator, and now I can predict how that person would work again, right? And even with a different design, right? So we can try to generalize. What's nice about this Bayesian approach is that they give what is called a posterior distribution. They say that for this person, this combination of these two parameters is the most likely. You should not consider this black space because it doesn't make any sense. This is very valuable in trying to understand complex user behavior. Now where you can apply this is what we coin ability-based optimization. This is building on Jake Wobrock's ability-based design, but trying to do that with computational methods. So what we try to do is we try to model individual differences such as these in these parameters of the models. So we have, let's say, a model that is producing human-like text entry performance, and it has parameters that are describing, for example, tremor or working memory capacity, and we can tune those values or learn those values from data, and then we can generate, we can give that to an optimizer that then can generate that person-like behavior. So here is the hand-eye coordination of simulation, typing in Finnish some text in English. And you see that how the hands and eyes would be moving as predicted by the simulation. And now you can go and you can ask, well, what would be the best design, for example, for a person who has tremor or dyslexia? And that's what we did in a recent paper. And then we showed that for users who have severe tremor, they have hard time writing with this, and this is well known. They make 50% errors. They're still very slow. They're like two words per minute, very, very slow. With the optimized design that groups letters like this and uses word prediction lists like this, then they can type a little bit faster, but what's more important is that the error rate goes down to like close to zero, so they can type adequately with this text entry method. Finally, I just want to say what happens when you bring all of these together, and that's what we call self-optimizing designs. So if you have inference and optimization and prediction together, you can make interfaces that are just taking care of themselves. This is one of the first things that we were doing, are just menus that are learning from the user and optimizing themselves in terms of reordering, highlighting, and grouping elements so that they can be more easily found. Here's another one that we just published this year. It's called familiarization. Everybody knows the notion of consistency. Now we can make an interface consistent to your visual history. So we know that you've been looking through these sites in the past, and we parameterize a visual search model to that history. And then we ask that if you were to look at this page and you were to look for this email over here, where would you look first? Would you look over here or somewhere else? And we go through all the elements and we reorganize in the browser before the user has seen the page. So we can make this, let's say, familiarized experience of the web to that person. So the items will be found where the visual history predicts that they should be. And this is 25% faster in terms of finding these commonly used items. To conclude, if I again want to go back to Cross's vision of AI in design, and he made these propositions that in the future there would be support for design, we would be able to emulate design, We would maybe rather want to learn something about design cognition, and maybe machines would be able to do some tasks that are really hard for humans. I think we're close to that point. This takes us back to this diagram. So weak AI is saying that we're able to delegate certain tasks and support the designers. Strong AI is saying that there would be design thinking capable AI in the future. And what I believe in is that then we're able to already pretty soon delegate these well-defined combinatorial problems to AI, not just routine tasks, as Susan was saying, but even very hard tasks. Moreover, we're supporting designers by giving these tools. We're able to embed designers' knowledge and theories directly in these adaptive interfaces and adapt them using that knowledge. And we're able to also assist in the interpretation of complex behavioral data. So what do I believe about strong AI, or I call them ADI, artificial design intelligence? And that's the claim that there would be machines that are able to do successfully any intellectual task that a human designer does. And to answer this question that I wanted to answer, I went back to one really nice summary by Johansson Schölbeck on what design thinking is, and gives 5 varieties. So design thinking is the creation of artifacts, it's a problem-solving activity, it's a way of reasoning and sense-making, it's reflective practice, and it's creation of meaning, and it characteristically uses imagery and sketching iteration. And I was going back to the results that we have obtained and other groups have obtained, and I made this quite conservative claim. I believe that here we're already having some progress. Our AI is generating some designs that are usable. It is doing problem solving with and without the designer. It is assisting designers in reasoning and sense making. It is not here. It's not in reflecting what the design work itself should be about. It is not yet creating meaning via design. And why is that? I was thinking about that. I was reading some philosophy of design, and Susanna also already mentioned the Vinograd Flores book from the 80s. And I think it has a very, very good insight there that when we're designing, we're actually designing for the listener. The listener is interpreting the linguistic and symbolic arguments that the design does. And that's really hard to automate in any way. The Dreyfus argument is maybe something that gives a further dimension to that. And it says that human-like being in the world and social acculturation is required for real intelligence. And if you go back to a regular design, this is Gmail. So what we're able to do, we're able to sort out the visual, spatial, motor aspects of design, but not really what kind of labels or icons or metaphors you should be using. And that's why, given these very hard limitations, what we've been trying to do is to find ways for AI to support. This is really fresh. Janine Koch is working on collaborative AI in design. This is a really hard problem called mood board design. And she has a cooperative bandit system, an AI system that is trying to recognize what the user is doing here and propose good additions to the design here. So the designer is searching here as normally some images and doing a mood board, and then the AI over here is making suggestions. But the designer always selects them and drags them over here and edits them. So this is one concept where AI can support without replacing or overriding, that leverages on human ability to recognize good designs rather than overriding the decision making. But what I'm really most excited about is this notion that we're actually developing new form of theorizing about interaction and design. We're formulating, for example, new principles of how menu interaction works and try to implement it in such a way that then we can produce, using that knowledge, real menus. It gives us also explanation why design is so hard, why we fail so often with design, not only for humans, but also for computers. Right? So it's because there are so many ways to infer what people are doing, and if you fail in that, that's going to propagate to the other ones. There's so many ways to choose a design. I showed these amazing numbers. And there are so many ways you can fail to predict the consequences of your design to users. And all of these are interconnected. All of them must work together in order to get the good design out. So finally, I think we need to deepen our engagement with AI. It's not sufficient to just work with AI and AI researchers. It's not enough to just demonstrate new interactive capabilities, but we should go to levels 3 and 4 where we offer these methods that then anybody can use. Similar as they have TensorFlow, we should be offering the TensorFlow of HCI. And finally, we should try to formally describe what human-computer partnership or convergence means, and implement those theories in the code that runs AI. And that's my takeaway for humanizing the AI. Thank you.
So even though we're running into lunchtime, I think we should have some questions because I think this is super interesting. Yeah, Kalle.
Have you been thinking about combining the two last things? So how you should do design so that your systems become more predictable?
Well, that's another objective function, isn't it, right? It's just a meta-level thing. I didn't mention about this self-optimization work too much, but what we're working on the idea of co-adaptation. So some of these, what I call computational rationality models, they predict how people learn and adapt their behavior as a function of design and their own goals and so on. Now what you can do is you can allow the computer to predict how the user will change its behavior when the design is changed, right? So that's somewhat toward that goal, yes. But it's really, really hard because it's not just this problem that I showed, but it's the additional layer of people predicting and changing the behavior on top of all of this, right? So the unintended consequences aspect of it.
So we have a question at the back. Carrie's running.
How many users do you need to predict a behavior? How many do you have to try it out on?
It depends. It can be 0. If you're lucky and find a theory from the literature, you don't need any users yourself. Right? If it's a common sense thing that people have certain capabilities, you can just put it in. But for many interesting abilities, you need, of course, statistical power in order to say something meaningful in the model as well. And that the answer to that depends. Right? What we try to do is we try to build on existing models that have substantial evidence behind them. So, for example, in psychology, they've done many, many replications of these studies and found this phenomenon to be real. So it depends.
One more, and then we're going to have lunch.
So my question kind of cuts across all the talks we've heard so far. You talked about prediction of complex human behavior. And when we move from prediction to manipulation of human behavior, as we've seen with some recent examples, there you come into a territory where there are conflicting ideas about this goodness function that you mentioned. So we've heard success stories so far in all the talks about how this works well in terms of efficiency and getting a task done faster, etc. But what about conflict in terms of competing interests, which could be equally valid mathematically in terms of whether making a user stay longer on a page or environmental versus societal interests? So how do you say AI would respond to that?
I don't think it can that well. I mean, this is an extra systemic aspect. I mean, you cannot easily construe political and ethical choices into the system like this. What you can maybe do is you can ingrain some controls and behaviors that might support that. One of the most rudimentary ones is the kill switch. You can switch off the IA. But there are more subtle ones, such as the alignment theory that has been developed in Berkeley, where they try to ensure that the goals of the system, AI system, are aligned with the inferred goals of the human, right? To ensure that they are not conflicting. So there are techniques that can allow you to infer them and align accordingly. But I don't think there's a good answer to that.